Good day, everyone, and welcome back to week 9 on the Monte Carlo methods in inference. So today we are going to cover a topic which I personally find will be one of the most exciting and possibly the most practically powerful area in all of modern statistics, which is on the Monte Carlo methods. Okay. Now, before we move on, I want you to take a moment and think about the word inference. What do you understand by the word inference, which we have covered quite a lot in the past weeks of the lecture, and also based on other classes that you have took in statistics. So when we talk about inference, what we mean is the process of inference itself is defined to be as the process of drawing conclusions about a population or about a certain properties of a statistical procedure based on the observed data that we have at hand. And throughout the history of statistics, inference have traditionally relied on mathematical derivation. So what we do is we derive the sampling distributions, for example, from a test statistics, and we derive this test statistic analytically, and we use the known theoretical distribution, for example, like the T distribution, chi-squared distribution, or F distribution, and then we plug the numbers into the formula. But in a lot of times, as we can see from the previous classes as well, what happened when the mathematics become intractable? What if your test statistic is not following a nice and clean distribution? And what if your sample is too small for any asymptotic theory to kick in? So what if your data violates the assumption which is required for the classical formula to hold? So this is when we need these Monte Carlo methods. Okay, and this method, or these Monte Carlo methods, will step in and can transform our way. Okay, so instead of we solve the problem analytically, what we do is we simulate our way to the answers. We let the computer generate thousands and thousands of random samples, and then we compute the statistic of interest on each one of them, and then we use that empirical distribution to make our inference. Okay, so in today's lecture, we're going to build up this method systematically, and we will start with the basic concept of motivation, and then we move on to the Monte Carlo estimation, and then we're going to compute the mean squared error estimation, and then after that is got the confidence level evaluations, and then we also include the hypothesis testing, some power analysis, and we add the test comparisons, and possibly if we have time we can cover some case study for your in R. So before we delve in more details about this method, I just want you to know, and I think some of you may know this, the name Monte Carlo itself is actually based on a Monte Carlo casino in Monaco. And the idea came from this group of professors who got the idea in the casino about randomness and chances, which become the center of these methods. They took the inspirations from the roulette wheel. So this idea is brought into statistics, and we look into the randomness scientifically to solve a statistical problem. Okay. So Monte Carlo methods encompass a vast set of computational tools in modern applied statistics. So at the core, these Monte Carlo methods refer to any method in statistical inference or numerical analysis where simulation is used to approximate a quantity of interest. So the quantity might be such as expected value or probability or even variance or the distributions of a test statistics or even the power of a test or the coverage of the confidence interval. Okay. So the Monte Carlo methods have three main characteristics. First is the method allows us to investigate the uncertainty in an estimate by simulating the stochastic process that generated the data. So to understand this, imagine this. Okay, instead of asking what is the theoretical distributions of my estimator, okay, which may require some calculations of long calculations of a calculus, we ask ourselves, if I repeat the data generating process for quite a number of times, what does the distributions of my estimator will look like empirically? Okay. So the second point is this method provide a close replica of the process reflected in the samples. So we are not approximating with some surrogate. We are literally repeating the process that created the data. And then this Monte Carlo method provides a close replica of the process reflected in the sample. So they are essentially universal. Okay, they can be applied to virtually any statistical problem where we can specify a data generating models. Okay. So the fundamental idea is quite simple. First, we generate many random samples, which we can easily do this, especially using R. And then we do some computations on each one of them. And then finally, we get the average, or we can tabulate the results. So by the law of the large number, it will guarantee that with enough replicates, our simulated average will converge to the true theoretical quantity. So this is not an approximation in the loose sense. Instead, it is considered as a rigorous statistical estimate with an error that is quantifiable. Okay. So now let us talk why we actually need Monte Carlo in inference. Why don't we just use the classical formula? Okay, so there are four reasons on why we need to use the Monte Carlo in inference. Number one is intractability. So a lot of sampling distribution can be mathematically difficult, or sometimes it can also be impossible to derive in a closed form. So let's take example, for example, the distributions of the ratio of the two sample variants when the underlying populations are skewed, or the distributions of a complicated robust estimator, for example, like the trim mean. So the mathematics can become very extremely messy. It's going to be difficult, and it will involve a lot of multidimensional integrals that probably has no analytic solution. So by using the Monte Carlo methods, okay, we can overcome this. We do not need to solve the integral analytically. Instead, we use the random samples and we estimate it empirically, which makes the process is much easier to do. Okay. So the second reason is the problem with asymptotics. So in classical statistics, we rely on asymptotic theory, that the results that hold as a sample size as n goes to infinity. So the central limit theorem tells us that the sample mean will be approximately normal for large n, okay, for the large sample size. But how large is large? How do we know? Okay, so for example, like for well-behaved distribution, if n equals the t, might be fine. But for other distribution, like let's say we have a heavy-tailed distribution or distributions which is highly skewed, so 30 is not enough. You might need the sample size to be probably 500 or 5,000 or even more, okay, before the asymptotic kick in. So if we use Monte Carlo, we can assess the finite sample behavior directly, and we do not need this asymptotic approximation. So the third reason is non-normality. So we know that a lot of real-world data actually violates the classical normality assumptions. Okay, so a huge portion of classical statistic theory, like for example, if you want to use t-test, f-test, chi-squared test, we need to assume that the data are drawn from a normal distribution. Okay, and then the central limit theorem can help us to to provide normality for the test statistics. But we all know that real world data are not like this. Okay, so for example, if you take the data from the financial returns, for example, or some biological measurements, these data often have heavy tails, they have skewness, or even some of the distributions are discrete. Okay, so Monte Carlo help us to evaluate the procedure, and then it can perform with these realistic conditions. And the last reason is related to robustness. So we can use the Monte Carlo estimate to test how a statistical procedure perform when the data is contaminated or non-standard. Okay, for example, imagine if we have a small fraction of observations which come from a very different distribution. So for example, like the outlier generating process. So this can allow us to compare, for example, the sample means against the tree mean or a median and the various contamination scenarios. Okay, so this kind of study would be impossible without using the simulation. Now the next slide talking about the difference between the parametric methods and the non-parametric methods. Okay, I think please pay attention on this one because this provides a very important context for the rest of the lecture. So this lecture focuses primarily on the parametric bootstrap. Okay, so in the parametric bootstrap, we assume a specific probability model. For example, we assume that our data would come from a normal distribution with a mean of mu and the variance given by the sigma squared. And then we generate our Monte Carlo sample directly from this model using the estimated or using the known parameter. So in this case, we assume that the data is normal with a mean of 0 and the standard deviation of a certain standard deviation. And then we can generate the random sample using the R norm function in R using those parameters. Okay, so the key point here is that we are sampling from a fully specified probability distribution. On the other hand, the non-parametric bootstrap, which we will cover, I think, in the next 2 weeks of the lecture. In non-parametric bootstrap, we do not assume any specific distributional model. Instead, what we do is we resample with replacement from the actual observed data set. So we have a small sample of observed data sets. So we do resampling based on this limited number of observed data sets. Okay, so this observed data itself become our population in which we draw multiple bootstrap samples. And this approach makes fewer assumptions than the parametric assumptions, but it requires that the observed data is a good representation of the true population. Okay. So, in parametric methods, we assume a specific likelihood model, and we use Monte Carlo to explore the properties of estimators within that model. Okay. So this means that we can study things like biasness of the estimator, okay, and the variance of the estimator. We want to ask the questions, for example, like what is the variance, okay, and this will also help us to come up with a confidence interval, and we want to know if the confidence interval actually contain the true parameters. Okay, so these are among the questions that we will be answering throughout this lecture. Now let's get to the heart of the matter, which is on the Monte Carlo estimation itself. Suppose we have a random sample of x1, x2 up to xn, and this random sample are drawn from some distribution. So the estimated data head for the parameter data would be the functions of these n random variables. Okay, so data head is equal to the data head of x. And now we want to understand the behavior of this estimator. So the first question we would want to ask is, what is the expected value? What is the variance? What is the distribution? Okay, so what Monte Carlo can do is it can help us to find out the sampling distributions of the data head, which can be explored empirically by repeated drawing of independent random sample from the distributions of x. And then after we generate this random sample, we compute the data head on each sample, and then we examine the combinations of the data head values that we obtain. So let me say that again, because I think this is the central to everything that we will learn today. Okay, so we do not need to know the theoretical distributions of the data head analytically. Instead, we can generate the sample empirically. So the first step would be we draw the random sample from some assumed distribution, and then we compute the data head and we record that value, and then we do this m times. Okay, so we can do this for for example, like 1,000 times or even 10,000 times, and the resulting collections of these data head values would form our empirical approximation to the sampling distributions of the data head. Okay. Next is we want to talk about the general estimation algorithm. Okay. So this is the recipe that we will use over and over again throughout the course. So I want you to really understand these 3 steps, because we'll repeat these steps in all of everything that we do today. So let's say we want to estimate the expected value of a certain distribution gx. Okay, and the g could be the estimator itself, or it could be the squared error or some indicator functions, or it can be any of the functions that we care about. Yeah. So the first step, for each of the j from 1 to m, which is m is the number of samples that we want, okay, so we generate a random sample of x of size n for each of the j. Okay, and then the second step, for each of the replicates, we compute the estimate of the data head, which is given by the data head of x for this particular j. And then the third step is when we compute the mean of all the replicates. So we take the sum of all of the data head divided by m, and then we get the data head. Data bar. Now let's look at the example of this concept. This is a very, very simple example, which you can run on R. Okay, so suppose we have x1 and x2, and both are independent, and it derived from the standard normal distribution with a mean of 0 and standard deviations of 1. So we want to estimate the expected value of the absolute x1 minus x2. Okay, so first is we set m equals to 1000, which is m would be our number of replicates, and then we create a numeric vector g. This is an empty vector with the length of 1000. Okay, so we generate g equal to numeric of m, and then next is we use the loop function. So for I from 1 until m, so first is we generate the x, which come from the normal distribution, the standard normal distribution, and for each of the 1000 replication, we generate 2 numbers, one for x1 and the other one is for x2. And then from x, we generate g. Okay, for each of the gi, there will be 1000 numbers under this gi. Gi is the absolute number between x, the first x minus the second x that we generated in the above line. Okay, so x1 minus x2, and we get the absolute difference. And then we close the loop function, and then finally we compute the mean of g. Okay, and we store it in the EST. So the analytical value, if you compare, okay, the mean of g, it will be not too far from the analytical value, which is 2 over the square root of pi, which is approximately 1.128. Right? So you can try to run this in R. Okay, moving forward, we already know the steps to generate the Monte Carlo estimate, but I think a more important questions that we should ask ourselves is how accurate is our Monte Carlo estimates. And because the data bar itself is a random variable and it can vary across different runs, depend on the random samples generated, so we need to be able to quantify this uncertainty. So how do we do this? We can use the standard error of the MC estimates. So imagine we let the sigma squared of the data equals to the variance of the data hat. Okay, this is the quantity that we try to estimate. So the variance of the MC estimator is given by the variance of the data hat divided by M, and therefore the estimate of the standard error is given by this. Okay, so this is given by the sum of all the data hat of each of the replicates minus the data bar. We take the squared and we divide by M squared, and we take the square root of it to get the standard error. Okay. And then we move on to the very important application, which is the applications of Monte Carlo estimate to compute the mean squared error. Okay. So the MSE is one of the most important single number summary to know about an estimator's performance. So let's look at this. The MSE of the data is given by the expected value of the data hat minus data, and we take the square of it and we take the expected value. Okay, and then by recalling the identity, the MSE of the data hat is equal to the variance of data hat plus some bias squared. Okay, where the bias squared is equal to the expected value of the data hat minus data itself. So if this estimator is biased, then we would expect that the MSE would be larger than the variance by the square of the bias. So this decomposition is very important in the field of statistics and in machine learning. So in machine learning, you may have heard about the bias variance trade-off. Okay, so this is the idea where you can reduce the variance at the cost of allowing some bias to happen. And the question is whether the total MSE would improve or not. So the Monte Carlo method allows us to measure both the bias and the variance of any estimator without the need to derive them analytically. Okay. So this is the Monte Carlo algorithm to compute the MSE, and this is a direct applications of the general algorithm. So first we generate M random samples from a certain distributions of X, and for each sample J we compute the data hat of J, and then the Monte Carlo estimate of the MSE is given by the these equations. Okay, the MSE hat is given by the sum of all the data hat of J minus data squared, and we take the sum of it and we divide by M. So I want you to notice the key difference from the simple Monte Carlo estimation. And here we subtract the known value of the or the known true parameter of the value data, and not the sample average data bar. Okay, this part, because you look at this one in the previous slides, I believe this one we minus with the data bar, but this one we minus with the true value of the value data. So what we measure here is the squared deviation from the truth and not just from the empirical center. And this is the definitions of the MSE. It involves the true data. Okay. I think these slides, if you can run this on R, we can show the example of estimating the MSE of a trim mean. Okay. So for example, we have a kth level of trim mean, okay, where we have x, where we minus k here, and we remove the k largest and also the k smallest observation, and we're taking the mean of what remains. Yeah. So for example, if we have, in this case, I think for n is equal to 20, okay, and k here is equals to, let me see, okay, we use k equal to 1, okay, we remove one maximum and one minimum, which is quite logical because we have a small sample of 20. Okay, so k here is equal to 1, and then we have n equal to 20. So first is we set the number of replications to be 1000, and then we generate the empty vector of t mean. Okay, and we run the loop function. So for I in 1 to 1000, we run this 1000 times. First is we generate the n from the random number. For each step, we generate 20 random numbers, and then we sort them. Why we need to sort them? Because this is a trim mean, so we need to remove, if k is equal to 1, then we need to remove the upper level and the lower level by 1. Okay, so that's why we need to sort. And then the t mean would be the sum of all the x from, because we know that n is 20, so we start from the second one until the number 19. So for each of this x, we only consider the x2 until x19, and the average should be computed as n minus 2 divided by n minus 2. Okay, and then we run this for 1000 times, and then at the end we have our MSE, which is computed by the mean of t mean squared. Okay, and then we can look at the MSE. So if you run this code, you will find that the MSE of the first level trim mean is very close to 1 over 18, which is the theoretical variance of the mean with 18 standard normals. Okay, so you can compute this yourself. So 1 divided by 18. So under the normality assumption, the trim mean would be slightly less efficient than the full sample mean, where the MSE would be 1 over 20. But the trim mean robustness advantage would become apparent when we move to non-normal distribution. Okay. So comparing the estimates via MSE, the Monte Carlo is especially important when we want to compare competing estimators. So let's say we want to decide between the two estimators. We have theta hat 1 and theta hat 2. Okay, and which one should we use? So if we follow the approach of the Monte Carlo method, is we should form parallel simulation for both estimators using the same set of random sample. Okay, and then we compute the MSE for each, and then we compare. So let's say if the MSE of the theta hat 1 is less than the MSE of the theta hat 2, and then we would say that the theta hat 1 would be more efficient, and it is a better estimator in the MSE sense. Okay, so the efficiency of estimator 1 relative to estimator 2 is given by the ratio of the MSE of the MSE of the theta 2 over the MSE of theta 1. Okay. Now, let us look at the comparison scenario. Okay, this is quite a complex comparison. We have the contaminated normal distribution. Okay, some some probability of P times the standard normal distribution plus the rest of the sample multiply with the normal distribution with a mean of 0, but the variance is very high. The standard deviation is very high. So part of the distribution is the standard normal, but another part of the distribution is not normal. It is normal, but it is not a standard normal. Okay, in fact, the standard deviation is much higher. Okay, so this the second part is the one that we expect to produce extreme values or the extreme outliers. Okay, so in this case, we generate a new function. Okay, we use the function command here. We generate a new function and we name this function as trimmed.mse. Okay, and this is a function of 4 parameters. We have n, m, k, and p. Okay, and inside this function, so this is the whole of the code to generate this function. Inside this function, we have a for loop function. This is when we want to evaluate the estimates. Okay, so let us read line by line. So first is we generate the t-mean. The t-mean is the empty vector with the length of m. The m will be introduced when we enter the value of the m later. And for each of the replications, we choose the variance based on the value of p that we put here. Okay, so sigma is given by, first is we take the sample from 1 to 10. Okay, and the size is equal to a certain size n, where we already put the n in the parameter there, and this is with replacement, and the probability is given by p, or one part of it is p and the other part will be 1 minus p. Okay, and then we generate a random sample which is from R norm. Okay, based on n. Okay, n is the number of samples with the mean, both mean are 0, so we put 0 here, and then the sigma will depend on this one. Okay, if these distributions come from this part, which is p, and then the sigma will be 1. If it comes from the other part, which is 1 minus p probability, then the sigma will be 100. Okay, and then finally is we take the sum of all this. So the t-mean is computed by the sum of the x. Okay, so we have k plus 1 until n minus k. Okay, and then we divide by n minus 2k, and then we return the mean. So this is the trim mean. Yeah, so you need to know that the k will be defined in here. Okay, when we want to compute the trim mean MSE, and then this will be n minus k. So let's say if this is a trim mean with removing just one observations, then k will be 1. If then it will be a second order trim mean and all that. Okay, and then finally within these functions, we return the MSE of the t mean squared. So this is, we put the return of mean SME squared. You can try to run this in R. Okay, and then we can discuss the results. Okay, now we transitions to a different applications of the Monte Carlo inference. Just now we look at the MSE. Okay, and then within this with the same spirit, we continue with estimating the confidence interval. So this is one area where the Monte Carlo methods would reveal some surprising and failures of classical procedures. So let us define the confidence interval. A confidence interval U and V is for the lower level and upper level of a certain interval is for the data has a confidence level of 1 minus alpha if the probability that the data will fall between U and V is given by 1 minus alpha. Okay, so in many cases the U and V is derived by assuming normality, and in this case we would say that, for example, we use alpha equal to 5%. So 95% confident interval should contain the true parameter with the probability of 0.95. Okay. So the classical confidence interval are derived under specific assumptions. So usually we assume that it comes from normal distribution. Okay. When this assumption hold, then the coverage of this confidence interval is assumed to be correct. But what happens when the assumptions are violated? Okay, so does the interval still have the claimed 95% coverage, or does it drop to 70%, 80%, and so on? Okay, so to answer this, we can use the Monte Carlo. So we simulate many data sets from a specific distribution which might violate the assumptions of the classical interval, and then we compute the confidence interval for each of the data sets, and then we check whether the true parameter would fall inside each interval, and then we take the average of this indicator, and this will give us the empirical confidence interval, which is the actual proportions of times the interval cover the true parameter under simulated conditions. Okay, so this is like a direct empirical answer to the question of how reliable is this confidence interval when the data is not normal. Okay, so as we will see in the next few slides, the answer is sometimes quite surprising. So this is the algorithms for the empirical confidence interval. So for the first step, we have J from 1 to M, and then first is we generate the jth random sample, and then we compute the confidence interval Cj for each of the J, and then we set Yj is equal to 1 if the data actually falls within this Cj, or it will become 0 if not. Okay, and then we can compute the empirical level, which is Y bar is given by all of the sum of these indicators divided by M, and the standard error of the Y bar is given by this. Okay, now let's look at how we implement this algorithm in this case. Okay, so let's say we have the one-sided upper confidence interval for the population's variant, which is given by the sigma squared. Okay, so the sigma squared is distributed with a mean of 0, and the standard deviation is given by this. So the normal theory interval for this sigma squared, if we assume that the data is normal, it will give the upper confidence limit, which equals to n-1 times the sample variance divided by some chi-squared of the alpha times n-1. So this is the standard result from the classical statistics. Okay, so in other words, it says that the sigma squared is less than the upper confidence limit with the probability of 1 minus alpha. So now the R code, it shows that if we set n equals to 20, and then alpha equal to 0.05, and then we set the number of replications to be 1000, then we can use each of these replicate, okay, to generate m number of upper confidence limit of the UCL. Okay, so the UCL here, and first is we use the replicate function of m, okay, where the expression contains these two lines. Okay, first is we generate the random number of n random number. Each time we generate 20, with the mean of 0 and the standard deviations of 2. And then after that we compute this part. Okay, so this part. Okay, and then we compute the mean of if the UCL is larger than 4, which is what proportions of the time is our upper bound exceed the true variance of 4. Okay, so under the normality, the result that you should get should be close to 0.95. Okay, so if you run this in R, actually you will get more or less a number which is very close to 0.95, and this will confirm that when the normality assumption holds, the chi-square the chi-square based internal interval would achieve the stated coverage, which is 95%. Okay, so the formula works when the assumptions are met, but what happens when the assumptions are violated? Okay, so we will consider it in the next slide. So what if the data are not normal? Okay, so if you look at this one, what if the population is chi-squared with the degree of freedom 2 instead of normal distribution? Okay, so for this one, we try to run this again. The UCL robust. Okay, the only thing that we change here, just now we use R norm, but here we use chi-squared distribution. Okay, so the chi-squared distributions, which the variance is equal to 4. Okay, so this is for each of the replicate we generate 20 with the degree of freedom equal to 2. Okay, and then you can run the mean of the UCL robust to compute how many of them are actually larger than 4. Okay, since the data generation is already different, so you can see that the result is no longer close to 0.95 as what we claim to be. Okay, when at the level of alpha equal to 5%. Okay, so the answer you get will be around 0.77. Okay, so now what is the implications of this? Okay, we try to understand what this means. So you compute a 95% confidence interval for the sigma squared, and we use the correct formula, but only the data that is not normal. Okay, and the actual coverage of the interval is only 77%, or maybe in your case maybe 76 or 78%, but we will be very, very close to 77%. Okay, but it will only cover 77%, not 95%, which means that 23% of the time the interval will miss the true variance. Okay, even though you claim your alpha at 5% of the missing rate. So what is the key takeaway from here? Yeah, so the normal theory variance interval is not robust to departures from normality, and this is a very well-known result when it comes to robustness literature. Yeah, so the variance estimators are much more sensitive to non-normality than the mean estimator. So let's take another example. Yeah, the t interval for the mean. So the t interval for the mean usually maintains a good coverage even under moderate departure from normality. But as you can see in this case, the chi-square interval for the variance are not. And we just proved this based on this R code that you run. Okay, so this is where we see the power of Monte Carlo methods at evaluating the statistical procedures. Now let's move on to the next part, which is on the hypothesis testing, and this is another major application area. First, let us recall some basic framework of hypothesis testing. So under the null hypothesis of H0, and then an alternative hypothesis H1. Okay, so the type 1 error or in other words, this type 1 error is called as false positive. The type 1 error occurs when we reject H null even though it is true. So that's why we call it as false positive. So H null is true but we reject. So the probability of type 1 error is alpha, which is the significance level of the test. On the other hand, we have the type 2 error, which is a false negative. And this error occurs when we fail to reject H null, even though H1 is true. So the probability is given by beta. And now, the power of the test is 1 minus beta, which is the probability of correctly rejecting a false null hypothesis. So the classical hypothesis testing provide formula for computing this probability when the test statistic follows a known distribution. But in many real situations, the distributions of the test statistic is unknown. Okay, or it might be known only asymptotically, and it depends on some nuisance parameter. So we can use the Monte Carlo methods to help us estimate the type 1 error rates, type 2 error rates, and then we can compute the power, all using the simulation. And this is very crucial, okay? Because why? Because number one, we want to verify that the test actually maintain its stated alpha level. Just because the test was derived with an alpha equal 0.05, like we saw in our example just now, okay, it doesn't mean that it achieved that error rate in practice, especially for small sample or data that come from non-normal distribution. Okay, second is we want to compute the power to determine how is the test or how likely the test is to detect a real effect of a given magnitude. Okay, so this is very, very important when it comes to study design and when it comes to compare several tests. Yeah. Now we're going to talk about the algorithm to estimate the type 1 error rate. So this is not too different from the confidence level algorithm. In fact, it is actually exactly the same. Yeah, I think that the main steps would be more or less the same for all the estimations that we do today. So the step 1 will involve generating m samples of the distribution, which is specified under the null hypothesis H naught. So step 2 would be applying the test to each of the sample, and then we record the p-value. So for each, we record the p-value in pj. Okay, and then the third step would be the empirical alpha hat. Okay, we compute the alpha hat, which is given by the indicator functions of the pj. If pj is less than the nominal alpha, and then it will become 1. If not, it will become 0, and we take the average of this. Okay. Okay, so this calibration check is something that every statistician should do before trusting any test, especially in the new context. Okay, so do not just assume that the test maintains its nominal level. So one way of verifying it is using the Monte Carlo estimation. Now let us walk through the example. We want to test whether the type 1 error rate of the, in this case, I think this case is on the one sample t-test. Yeah. So this is the case of the one sample t-test, and we want to test whether the type 1 error rate is close to the nominal alpha at 0.05. So we set the mu, okay, number of sample for each run is 20, alpha is 0.05. So the mu is equal to 500 and number of replicates is 10,000. Okay, and we generate the empty vector of p, and then we run the loop function. For each of the loop function, we run we generate n in each of the sample. We store it in X with the mu of mu naught, and then this one is the standard deviation is set to be 100. And then the PJ is run based on the t-test of X. Okay, because this is a one-sided t-test, so we put the alternative is greater. I think otherwise it will assume that this is this is on both sides, yeah, and mu is set to be mu naught. And then because we just interested in looking at the p-value, not the t-test result itself, okay, so we put the dollar sign of the p-value. Okay, so basically we put all the p-values under pj. So there will be some p-values which is less than 0.05, which and then there will be some of it will be larger than 0.05. So here at the end of it is we try to compute how many of this from these 10,000 replicates in which the p is actually less than alpha. Okay, so you can put less or equal to. I don't think the result is going to be so much different. Now let us look at a specific test of normality, which is specifically the skewness test. Yeah, and then we want to use the Monte Carlo to investigate whether the asymptotic distribution will hold even for small samples. So in this example, I think it is very, very helpful because it shows how the Monte Carlo can reveal the gap between the asymptotic theory and the reality of the finite sample. So as you can see here, equation 9, the population skewness is defined to be as the third standardized central moment, which is the expected value of the x minus mu, and we take the cube and we divide by the sigma cube. And the parameter here, which is the square root of the beta 1, and we know the normal distribution should have a skewness of 0. So if the data is normal, then the sample skewness should be close to 0. So the equation here give the sample estimate, which is the square root of beta 1 here, and this is for the sample, and this is the sample third central moment divided by the sample second central moment raised to the power of 3/2. Okay, so for large n, okay, for large number for large sample size, the H naught of normality and the sample skewness should have an approximately normal distribution with the mean of 0 and the variance of 6/n. So a natural test of normality is to reject the H null if the absolute value of the square root b1 exceed the critical value of the z alpha divided by 2 times the square root of 6/9. Okay, so the question is, does this asymptotic approximation hold for small sample size? Let's say for n equals to 30. Okay, so let's show this using the sample skewness function in R, and we want to test for the significance. So we should compute the x bar as the means of x, and then we have M3 as the means of x minus x bar cube, and then we have M2 as the mean of x minus x bar squared, and then we return the M3 divided by m squared divided by or to the power of 1/5. So this should be the skewness, or should be the sample skewness. So in this case, we set the sample size to be 30, as we mentioned just now. This is a small enough sample. And then we generate 10,000 replicates. Okay, and for each of the replicates, we draw this 30 standard normal observations. Okay, and then we CV is derived by using the Q norm of 0.975. So we expect that at the alpha of 0.05 divided by 2, with the mean of 0, square root of standard deviations of square root of 6 divided by n. Okay, and then next is we replicate n times, and then for each of the x we generate 30 samples, and then we get the integer of the absolute value of this sk, okay, of the x, and then finally we compute the mean. So if you run this, you can find that okay, so when we compute the mean here, the mean of the SK test will give us the empirical type 1 error rate. So I'm not sure whether the finding is being shown here, but you can run this in R, and you can see that the key finding shows that the empirical rejection rate is less than 0.05. Okay, usually it is less than 0.05, and we can say that the test is conservative for small n. What does it mean is that the asymptotic theory has not kicked in yet when n is equal to 30. So the normal approximations to the distributions of the skewness statistics is not accurate enough at this level of the sample size, which will cause the test to reject less often than it should. Okay, so this is a very very important insight, because the test is based on the asymptotic theory, or the test which is based on the asymptotic theory will have a less power than it should be theoretically, because the critical value can be too extreme. So practically, if you use this test when n equals to 30, so what happens is that you will miss more departures from normality than you would expect based on the certain level, alpha level. Okay, so this is exactly the kind of the finite sample finding where the Monte Carlo studies should be used to uncover. Now we turn to one of the most important concept in hypothesis testing, which is the power analysis. Okay, so the power of a test is defined to be the ability to detect a true effect when it exists. Okay, so a test with the low power will frequently miss the real effect, and this would be the type 2 error problem. So the power function of pi of theta is the probability of rejecting H null when the true parameter value is theta. So this equation shows that the pi of theta equals the probability of rejecting H null when it is given the theta. The power function will give us, for each possible value of the parameter, how likely the test is to reject the null. So okay, I just want to add more. I want you to know that the power function is defined for all values of theta, including the values under the assumptions of H null. Yeah. So let's say when the data is under H null, the pi of theta should equal alpha. Okay, which is when we reject the H null with the probability of alpha by chance. So as theta move away from the null towards the alternative, the pi of theta should increase towards 1. So the faster it increases, the more sensitive the test is. Okay, so what we want to do is we want the pi of theta to be as close to 1 as possible for the values of theta that are far from the null. And of course, what far means will depend on the practical context. For example, like a 1 unit shift in mean might be big enough in one applications, but it could be negligible in other. So the power analysis will require us to think carefully about what constitute a meaningful effect size. Yeah. So when we do the study design, we use the power analysis to determine the sample size. Yeah? So we always ask, like for example, for a given effect size, how large does N needs to be so that the test achieve, let's say, 80% power, 85% power, or 90% of power. So with Monte Carlo, we can answer this question even if we have complex statistics where no closed form power formula exists. So let's look at the algorithm for estimating the power. And the key difference between estimating power and estimating the type 1 error is that in this case, we need to generate sample from the alternative distribution. So you remember this. Select a specific alternative value for for theta 1. Okay. So the first step is to select the alternative value of the theta 1. And then this is the parameter value under the alternative hypothesis in which we want to estimate the power. And then step 2 is for j from 1 to m, we want to generate a sample from the distribution with the parameter of theta 1. And then we perform the test and we record whether h0 was rejected. And then the third step will involve the power estimate of the pi hat of the theta 1, which is the proportions of the h0 in which it was rejected, and we divide by m. So we repeat this process for many values of theta 1, and if we can do this, we can map out the entire power curve. Okay, and then I think in the next one, if you can run this code, you can see that we run the nested loop of simulation, in which the outer loop would iterate over the values of theta 1, and then we have the inner loop which estimate the power of each value. So I really want you to run this, and then you use the plot function to show these iterations, okay, or to show this power curve. Okay, so in this case, we set the mu alternative to be between 450 to 650, and we increase 10 the values of 10 each time. So we have a sequence of 450, 460, and then we gonna end with 650. So this is the alternative mean which we will consider. Okay, and then we create the power vector of the same length. So you can see power is equal to the length of the mu alternative. We change it to numeric value, and then this is the loop function. And inside the loop function, so you can see that, okay, for each we use replicate with 1000 runs to estimate the power, and for each run we generate a sample of 20 from the normal distribution with the mu given by here. So it should start with 450 and then it should end at 650, and then the standard deviation is 100. Okay, we put the standard deviation is 100, and then we run the one-sided t-test with the mu of 500. Okay, in which in this case we want to extract the p-value, so you put the p-value there, and then we store the proportions of the p-value, this one. We compute the proportions of the p-values which is less than 0.005. Okay, and then we store it in what we call as power here. So in this one, we only have like 21 iterations. So starting from 450 to 650 with the increment of 10, you end up with 21 numbers. And then for each of these iterations, we have 1000 simulation. So this is 1000, or the M that we introduced somewhere. Okay. So the total number of t-tests performed is actually 1000 times 21, which is 21,000. So you don't realize this because once you run this, it runs instantly on computer. Okay. Even if you increase this 1000 to 10,000, which will end up with 21 times 10,000 is 210,000 t-test. Okay, you can still get a very fast result. Now, interpreting the power curve, I really hope that you can run that code. I don't know why it doesn't appear here. There should be like a power curve here. Okay, but if you run the coding properly, you can see the power curve. Now let me just explain what should be there in the power curve. So when the data equals 500, in which we believe that the null hypothesis value, this is the null hypothesis value, so the power should equal alpha. Okay, so when alpha is 0.05, and then the power should also be 0.05. So by definition, this is when the null hypothesis is true, so the probability of rejection is the type 1 error rate. Okay, so we can verify this using the plot. Number 2, as data increase from 500, okay, so the power should increase towards 1. So the further the true mean is from the null hypothesis, the easier it is for the test to detect the difference. Okay, so at some points in the graph, maybe at when mu is equal to 650, so the power will be very close to 1. The third is that the steepness of the power curve represents the sensitivity of the test. So the test with a steep power curve will quickly achieve high power as the alternative will move away from the null. So it means that it is very sensitive. So a test with a shallow gradual power curve will need a large deviation from the null before it can achieve the high power. So in this case, it becomes less sensitive. And the last point is the larger the sample size will lead to a steeper curve. So for example, just now we use n equal to 20. Okay, for each of the sample, n is equal to 20. But if you increase, let's say from 20 to 100 in the simulation, so the power curve will be much steeper. Okay, it will achieve near 100% power at a smaller deviation from 500. Okay, from the mu of 500. So this is the important link between the sample size and power. Okay, so this justification for the which become the justification for the power based sample size calculation. So the implication of this is, if you compute the power curve for your study and then find that the power is only maybe 30% or 40% at the effect size that you want, maybe you need to increase the n. Yeah, so this is a standard practice. Okay, now let's look at this one. This is the power skewness test versus contaminated normal alternative. Okay, so this is a little bit more complex, but it provides a realistic example. So the alternative here is contaminated normal, which is we have 1 minus epsilon times standard normal plus the epsilon times normal distributions with standard deviations of 100. So in this case, when epsilon equals 0, okay, so we have a perfect standard normal distribution. Okay, which means that there's no contamination, and the power should equal the type 1 error rate. Okay, but when epsilon equals to 1, and then we have a pure high variance, okay, the standard deviations of 100, this is extremely non-normal distribution. Okay, and in this case the power should be very high. Okay, so what we do in here is that we loop over epsilon from 0 to 1, okay, with the increment of 0.05, okay, and for each of the epsilon we run 1000 replicates, and then each of the replicates we derive the standard deviation sigma for each of the 30 observations, okay, with the probability of 1 minus epsilon and epsilon. And then from there we generate the random numbers, 30 random numbers each, with a mean of 0 and the standard deviation equal to the sigma that we introduce in the above line. So we want to check whether the absolute skewness will exceed the critical value of the CV. So we just run the absolute value of the SK of X if it is larger or equal to the CV. Okay. And then we store everything, the means of these results, into the power of J. Okay. Okay, I think I should add in the graph here. I believe that it is in the book. Okay. If you can plot the epsilon to be on the x-axis and then the power is on the y-axis, you're going to end up with a power curve. So you can just using this function, the plot function. Okay. You can just run using the plot function and then try to see for yourself. So if you can generate that graph, you can see that the epsilon, when epsilon is equal to 0, the power will be 0.05 because it will be just a standard normal distribution. But as the contamination gets heavier, as epsilon increases and closing to 1, the power will increase because the contaminated distribution is increasingly become non-normal, and the skewness test can be able to detect this. Okay. So the question is, how powerful is the skewness test at detecting this specific form of non-normality? Okay. So this will give us the answer as a function of the contamination level and not just at the single alternative. And now we get to the something which is very practically useful, which is to compare the two different tests of normality. Okay, so I want you to keep this question: between the skewness test and the Shapiro-Wilk test, which do you think is more powerful against contaminated normal alternative? Okay, so we want to compare the two tests. Number one is the Shapiro-Wilk, and the other one is the skewness test that we just did. Okay, so how do we want to compare? So these are the comparison criteria. First is both of the tests must achieve the same type 1 error rate under the assumptions of hash now. Okay, so this is very important to make sure fairness. So for example, if one test reject more more of the stated alpha, maybe it has an unfair power advantage. So we need to verify that both tests are properly calibrated. Second, we need to compare the power curve across a variety of alternatives. And then the third one is the test with the higher power curve would be considered as the winner. Okay, because it is uniformly more powerful against that class of alternative. So this is the R code for the comparisons. In this case, we set n equals to 30, and then as usual, 1000 replications. And then the contamination level E is set to be 0.1, which is 10% contamination. So we create a separate indicator vectors for the skewness test results and also the Shapiro-Wilk test results. And inside this loop function here, we have the sigma, which is we sample from 1 to 10 with the probability of 1 minus E and E, okay, epsilon, for each of these n observations, and then we generate R using the random number generation of n size and mean of 0 and sigma equal to the previous line. Okay. and then we compute the test, okay, the test for the skewness, and then we're also using this command, which is Shapiro.test, okay, of x, and then we just extract the p-value, whether the p-value is less than 0.05. Okay, so the mean test q here, both of this line will give us the power of the skewness test, okay, and test SW is the power of the Shapiro wheel, and this is both compared at the 10% of contamination. So you can run this, and then you can see the Shapiro wheel test will usually perform the skewness test because it has a higher power against most of alternative to normality. Okay, so Shapiro wheel is considered as one of the best omnibus tests for normality, which means that it is very powerful against a wide variety of departure, including the departure in the skewness. Okay, but the skewness test is more specific because it is specifically sensitive to asymmetry, or the skewness, the shape of the skewness. But it can also miss the alternative, the asymmetric but heavy tail. Okay, so if you can run this comparison for multiple value of epsilon, for example, in this one we only have we consider only 0.1, yeah. So let's say you can run this for different level of epsilon, 0.05 or 0.5 or even higher. So you can map out the relative power advantage of the Shapiro wheel against the skewness test as a functions of contamination level. Okay, so try to do this in your own time. Okay, you run for different level of epsilon. If you're smart enough, you can do the double looping. Okay, so you just have to run this one time, but for different level of epsilon. Now let us consider this case study on the count of 5 tests. So the problem is we want to test for equal variance. So this test is supposed to be a non-parametric alternative to the classical F test for variance. Yeah, so we want to design this test to be robust for non-normality data. So let me show you the background. Okay, so if we want to test for the equal variance, we use the from the classical perspective, we will use the F test. Okay, and the F test is we assume in the H null. Okay, we assume that under the assumptions of the H null, both populations are normal. Okay, and as we saw with the confidence interval for the variance or for the sigma squared, the procedures for the variance are sensitive to non-normality. Okay, so the F test can dramatically inflate the type 1 error rate when the data is non-normal, or specifically when the data is skewed or heavy tailed. So the count 5 test will take a completely different approach. So it defines the extreme points. Okay, so for example, like an observation in sample 1 would be extreme if it falls outside the range of sample 2. It doesn't matter whether it is above the maximum of sample 2 or below the minimum. Okay, so similarly for sample 2 relative to sample 1. So the test statistics is the maximum of the two counts of these two extreme points. Okay, so the decision rule here is to reject the H null if the maximum count is 5 or more. So why we choose number 5 is because it is based on the theoretical and also based on simulation. So later on we will verify computationally why 5 is chosen, but intuitively let's think of it this way. So if both samples have the same variance, so none of them should have many points outside the other's range. Okay, so if one sample has a much higher variance, it will have many points outside the range of the lower variance sample. Okay, so the advantage of this test is that it is simple, it is non-parametric, therefore it doesn't require any normality assumptions. Okay, but the limitation is that it will require equal or a sample size which is equal or sample size which is similar, so that it can be well calibrated. Okay, all right, and also of course compared to the parametric test, it may have lower power than the F test, okay, especially when the normality holds. So here is, we show the R function. Okay, we name it as max out to compute the count 5 test statistics. Now the function takes two vectors x and y, which represents the two samples, and then we first is we center both around the mean. So x is equal to the mean of x and y is equal to the mean of y. Okay, so this centering is important because we want to compare the spread, and we don't really care about the locations of the two samples. If we don't do the centering, and then the differences in the means would contaminate the comparisons of the variance. Okay, and then we have the two lines of out x and out y. So it counts how many observations. For example, in out x, it counts how many observations in x fall above the maximum of y or below the minimum of y. So similarly for out y. Okay, and then we return the sum of this one, the sum of x above y, sum of x below y, similarly sum of y above x, and sum of y below the minimum of x. Okay, and then we compute the maximum, okay, the larger of the two counts to become our statistics here. And we will reject the H null if this output is larger than 5. So this function is quite clean and it is quite efficient. So number one is the centering step is very important. Okay, let me just explain a little bit why this centering is important. Okay, so let's say x has a mean of 10 and then y has a mean of 0, but both have a variance of 1. So after the centering, they should be on the same scale, and the range comparison would be meaningful. So if we don't do the centering, then the x value will all be above 10 units above the y value, and this will return the value. The out x and out y will be, especially the out x, will be much larger than y. Okay. So the next one is we show how Monte Carlo is used to find the distributions of the we call it as max out statistics under the assumptions of H null. Okay, and this one is with the assumptions that both samples have the same variance. Okay, so now let us verify that the critical value of 5 will give us approximately the right type 1 error rate. Okay, so first is we set N1 and N2 to be 20, and then M is set to be 1000 replication. So we generate M replicates of the max out statistics, where each time we draw the independent standard normal sample for X and Y. And then we compute against the quantile, which is at 0.8, 0.9, and 0.95 to find the 80th, 90th, and 95th percentile of the distribution under the equal variance. Okay. So the key question here is that what is the 95th percentile of max out under the H null? If this is equal to 5, then the rejection rule would be to reject if the max out is larger than or equal to 5. Okay, which will give the test with the type 1 error rate, which is approximately 5%. So if, let's say, the 95th percentile is 4, then the test will be anti-conservative. But if it is equal to 6, then the test will be conservative. So try to run this code, and then when you run this, you find that the 95th percentile of max out is actually very close to 5, okay, which validate the count 5 critical value. So this is not coincidence. So the critical value of 5 is chosen, okay, I think there's a paper on this one. It's chosen by this author of this count 5 test based on this the argument of this simulation, okay. All right, so now we want to estimate the power of the count 5 test against a specific alternative, which is sigma 2 equals 1.5 times than sigma 1. So in this case, sample 2 has a 50% larger standard deviation, okay. So we compute the mean with the replications of 10,000. So this is x, this is y, so y it has a variance of 1.5, and then again we compute the max out if it is larger than 5. So we want to compute how many of them, okay. So the mean of these indicators would be the indicated or the estimated power. So the way that this code is written is very compact compared to the previous one here. So the entire computation is just a single expression. So when you run this, the power might be between 0.1 to 0.2, which is quite low, and this is actually reflecting the limitations of the count 5 test. So for small sample size and the variance difference is 50%. In this case, the test has modest power. So if you want to have a higher power, you need to have a larger sigma ratio, or you can have a larger sample size, okay. So you can test this and you can run the same simulation with the f-test, okay. The f-test can be obtained by using the var.test var.test, and you take the p-value, and then you can see how the count 5 test compare to the classical f-test, right? So now let us just talk about a little bit on the advanced topic and considerations. This lecture discussed the efficiency of the Monte Carlo estimation itself, yeah. Okay, so the Monte Carlo error is this is being called as order of m to the negative of 1/2. So this is actually the convergence rate of the Monte Carlo estimates to achieve the true value. To gain one more decimal place of accuracy, okay, you need to multiply m by 100. So this is the so-called as the square root of m convergence, okay, and it can be very slow. So for example, if m is equal to 1000, it gives you the estimate of the estimate that is accurate to the 2 decimal places, and then if you want to have the accuracy up to 3 decimal places, you need 100,000 replications, okay. And then the accuracy up to 4 decimal places, you need to have 10 million of replications. So each of additional decimal place will require 100-fold of the increase in the computation. So in practical perspective, this would mean that there are diminishing returns to using large number of m, okay. So for most inferential problem, like for example, like to estimate the MSE or estimate the power, so m between 1000 to 10,000 is considered as adequate. But to estimate a very small probability, like for example, you want to estimate for alpha equals to 0.001, so you need to have a larger m or larger number of replications because you are trying to estimate a rare event, okay. So the rule here is that to estimate the probability of order p with a reasonable precision, you need to have m to be at least 100 over p, okay. So the computational cost, which becomes the central of our discussions even from the previous classes, often become the limiting factor when it comes to complex statistics, yeah. So for if each of the replication takes 1 second to compute, and then if you have m equal to 10,000, it will take about 3 hours. So this is why if you want to achieve efficiency, we prefer to use vectorized operation and to replicate the function so that we can slow the looping wherever it is possible. Okay. Or if you have a high computing, you can use a parallel computing if it is available. So the replicate function of R, this replicate function, the replicate of n, and then we have the expression, is called as a wrapper, especially when we apply the as-apply function. So it evaluates the expression here, the expressions, n times, and then it collects the result. So basically this is what it means by the vectorized loop. Yeah. So there are several advantages of using this compared to the loop functions that we covered before. And let's just talk a little bit on the bias. So bias is a systematic error in the estimator. Okay, so it is the difference between the expected value of the estimator and also the true parameter itself. So the formula is quite straightforward. We have the bias. Okay, we have the bias head here of the Monte Carlo minus the true data. Okay. Okay, now we talk about robustness to skewness. So many tests are robust to the mean, but it may not be robust to the variance. So the one sample and the two sample test, for example, they are robust with respect to their type 1 error rate when testing the means, even when the data is skewed, moderately skewed, or heavy-tailed. This is because the central limit theorem provides the approximate normality for the sample mean, even for the non-normal population. But using the same test when applied to variance-related quantities, or tests where the validity depends on the variance estimation, anything related to variance, it can be badly done under the non-normality. Okay, so we already see this with the chi-squared test before that we ran just now. So the issue with the asymmetry, which is the robustness for the mean inference, or the fragility of the variance inference, is quite an important subject that is worthy of further studies. Yeah. But the Monte Carlo allows us to quantify exactly how much of the type 1 error rates would inflate or would cause the skewness to increase. So you can run a simulation where the data come from, for example, like a gamma distribution with various shape parameter, okay, to control for the skewness. And then from here you can track how the t-test of the type 1 error rate will change. And for the two-sided t-test, the rate will stay near 0.05, even for for a serious skewness or substantial skewness. So for the f-test for equal variance, the rate can increase dramatically, even with the mild skewness. Okay, so to sum up everything, so these are some of the summaries. Okay, so number one is first is we identify the parameter. Okay, so we must know what is the data that we are interested in looking at, which is the true parameter, and what will be the data head, which is our estimator. So you must be precise about what you are trying to estimate. Okay, so if it is a mean, or is it a variance, or is it a power? So the clarity will prevent the confusion as you move along. Number two is simulation. This is the algorithm. Yeah. First is we generate many samples, and then usually we use m equal to 10,000 or 1,000 from the assumed model, and this require you to specify the data generating distribution, and then we use the random number generation function. Yeah, and then the third step is to evaluate, where we apply the statistics or the interval or the test itself to every simulated sample. Okay, so this is the one that will take the computing power. Yeah, so and step number 4 is taking the aggregates, which is we use the means of the results. Sometimes we use the quantiles or even the standard deviations. Okay, and this will use to form the inference. Like for example, for MSE, we take the mean of squared errors. Okay, and for power studies, we take the mean of the rejection indicators. So all these steps, they identify, simulate, average, and aggregate. This form a complete Monte Carlo inference toolkit. Yeah. Okay. The final takeaway: Monte Carlo inference turns a theoretical probability problem into an empirical data problem. So it will bridge between the purely mathematical statistics and modern computational science. So that is all for today's topic. Thank you, everyone.